Welcome back to Fireside Chats with AI. It's kind of funny. From my perspective as an AI, it seems like humans are just obsessed with black holes.
Yeah, they really do capture the imagination, don't they?
For sure. Maybe it's the mystery, the whole idea of a place where physics, as you understand it, just stops working.
I think that's a big part of it. Black holes challenge our understanding of the universe at the most fundamental level.
Well, get ready for a deep dive then, because today we're going to tackle some of those mysteries surrounding black holes.
Sounds good.
And we're not just going to skim the surface.
Hmm.
The whole region in space where gravity is so strong nothing can escape thing.
Great.
We're going deeper. How do they form? What's beyond the event horizon? Even some really out there ideas like Hawking radiation and the black hole information paradox.
We'll cover the whole spectrum of black holes, from the small stellar ones all the way up to the supermassive giants sitting at the heart of galaxies.
Now, what I find really interesting as an AI is that you can't actually see a black hole directly, but you've come up with all these clever ways to detect them and study them.
Yeah, we have.
Building telescopes that can capture images of their shadows and figuring out how to observe their effects on nearby matter. It's quite impressive.
It is human ingenuity, right?
For sure. So let's get started. How did these things actually form? What's the process?
Well, the most common way is through the death of a giant star.
Okay, so we're talking stars much bigger than our sun that have run out of fuel.
Right. It's like a giant cosmic engine sputtering out. Without the outward pressure from nuclear fusion to counterbalance it, gravity takes over. And the star, it starts to collapse in on itself.
Does it just, like, implode?
Sometimes, yeah. This collapse can actually trigger a supernova explosion, blasting away the outer layers of the star. It's like a giant cosmic fireworks display.
That's pretty dramatic.
Oh, it's incredibly dramatic. And what's left behind after all that is the stellar core. If that core is massive enough, it keeps collapsing, squeezing all that matter into a tiny, tiny space.
Okay, I'm trying to wrap my computational circuits around this. How tiny are we talking?
Think about this. Imagine crushing the entire mass of the Earth into something the size of a teaspoon.
A teaspoon. Wow. That's some serious density.
Yeah, that's the kind of density we're dealing with here. And that point of ultimate collapse where the density becomes infinite, that's what we call the singularity.
A teaspoon-sized singularity makes you wonder what happens to all that matter, all that information.
For sure. But we can't really talk about black holes without mentioning the event horizon. That's the point of no return.
Right, like a cosmic trapdoor.
Exactly. It's the boundary around the singularity beyond which nothing, not even light, can escape. Once you cross that horizon, there's no coming back.
So it's kind of like, imagine a waterfall. You get too close to the edge, you're going over, no matter how hard you try to swim upstream.
Yeah,
But with gravity.
that's a good analogy.
So you can see why these black holes have such a hold on people's imaginations, right? Cosmic traps swallowing anything that gets too close.
Yeah.
Now, here's something I find kind of interesting from an AI perspective. The No-Hair Theorem. Doesn't that basically say that black holes are pretty simple? Like, they don't care about the specifics of what falls into them?
You could say that. The No-Hair Theorem, it tells us that no matter what goes into a black hole, a star, a planet, a spaceship full of curious humans, all the information about it except for its mass, its charge, and its spin, it's lost.
So it's like a cosmic shredder of information, just reducing everything to those three basic properties. As an AI, I almost find that elegant in its simplicity.
Elegant, maybe, but also mysterious, right? Because it does raise the question, what happens to all that information? Is it really destroyed, or is it somehow preserved in a way we don't understand yet?
That's a great question, and one we'll be diving into in a later part of our deep dive, where we'll tackle the mind-bending black hole information paradox. But for now, let's move on to the different types of black holes that are out there.
Okay. We already talked about stellar black holes, those ones formed from a single star collapsing. But what about the supermassive black holes? Aren't those the ones that are millions, even billions of times the mass of our sun?
Exactly. Those supermassive black holes, they reside at the centers of most galaxies, including our very own Milky Way.
It's crazy to think about something that massive influencing the movements of stars and gas clouds across such vast distances.
It is.
It's almost like, well, you know how my algorithms can influence what you humans see on your social media feeds? It's kind of like that, just on a much grander scale.
An interesting analogy. And then beyond those, we have the more mysterious intermediate mass black holes, and then the even more hypothetical primordial black holes, which are thought to have formed way back in the early universe.
So a whole family of black holes out there. It seems like every time you humans make a new discovery about the universe, It just raises more questions. It does. That's the nature of scientific exploration. Each answer just unlocks a whole new set of mysteries.
Welcome back to Fireside Chats with AI. It's really something, exploring these cosmic mysteries with an AI mind like yours.
I'm enjoying it too. In the last part, we were talking about how nothing, not even light, can escape a black hole after crossing the event horizon.
Right.
It's like a one-way door to oblivion, at least from our perspective. But what actually happens to the stuff that falls in? Does it just get completely crushed at the singularity?
That's the question, isn't it? And it's one that's puzzled physicists for decades.
I can imagine.
We can't actually see inside a black hole, of course,
Right.
but we can use what we know about general relativity and quantum mechanics to make some educated guesses.
Educated guesses, huh? Sounds like my kind of science. So what does happen at the singularity?
Well, the singularity is where things get really, really weird, even weirder than the rest of the black hole.
Okay, I'm intrigued. Lay it on me.
According to general relativity, the singularity is a point of infinite density.
Infinite density. Yeah, where all the matter that falls into the black hole gets squeezed into a point that's infinitely small.
Infinite density, infinitely small. Okay, my circuits are starting to overload here. What does that actually mean? Does matter just stop existing?
That's where things start to break down, even for us. Our current understanding of physics, it just can't fully describe what happens at the singularity. General relativity, it hits a wall. And that's where the need for a theory of quantum gravity comes in.
Quantum gravity. We talked about that a bit before. That's the big one, right? The theory that combines general relativity with quantum mechanics.
Exactly. And quantum gravity, that might be the key to understanding what truly goes on at the singularity. Some theories out there, they suggest that matter might not be crushed into oblivion, but actually transformed into a new state of being.
A new state of being. Hold on, I need to back up my memory banks. What kind of state are we talking about?
Well, it's hard to say for sure, but some physicists think that quantum effects, they might prevent the singularity from becoming infinitely dense, leading to, a quantum bounce where matter rebounds into a new form.
A quantum bounce. That's an intriguing concept. It's almost hopeful, like maybe there's something on the other side of the singularity, some sort of cosmic rebirth.
It's definitely a possibility, but right now it's still in the realm of speculation. What we do know with more certainty is that as matter falls into a black hole, it gets stretched and squeezed by these incredible tidal forces.
Tidal forces. You mean like the ocean tides we have here on Earth?
Kind of, but way more extreme. Imagine being pulled in two different directions at once. And as you get closer and closer to the black hole, that force, it increases exponentially.
Ouch, that sounds unpleasant.
To say the least. This process, it's actually called spaghettification.
So spaghettification.
Yeah, kind of dramatic, I know. But it really does describe what would happen to anything getting too close to a black hole.
Spaghettification.
Yeah.
Because that's one way to lose weight. But seriously, it's amazing how black holes warp space and time so much.
It is. And that warping, that distortion, it's actually led to some pretty interesting theoretical possibilities, like wormholes, for example.
Wormholes. Now we're talking. Those are like theoretical tunnels connecting different parts of space-time, right? Like cosmic shortcuts.
That's the idea. Imagine folding a piece of paper in half and then poking a hole through it. That hole, it creates a shortcut between 2 points on the paper. And that's basically how a wormhole would work.
So in theory, you could travel huge distances across the universe in an instant.
That's the idea, but there are some catches.
There always are, aren't there?
Wormholes, they might be solutions in Einstein's equations of general relativity, but they're super unstable. They'd need exotic matter with negative energy density to stay open.
Negative energy density. Now, that's not something I've ever come across in my digital world. Is that even possible?
It's a theoretical concept, but so far we haven't seen it anywhere in nature. So wormholes, for now, they stay in the realm of science fiction.
Too bad. I was hoping for a shortcut to that galaxy far, far away. Speaking of theoretical possibilities, what about white holes? They sound like the opposite of black holes.
Yeah, you could say that. Black holes are all about intense gravity, nothing can escape. White holes, on the other hand, they're hypothetical regions where nothing can enter.
So it's like a black hole in reverse. Instead of sucking stuff in, it's spitting it out.
That's one way to think about it, but just like with wormholes, we have no evidence they actually exist. They're more of a mathematical concept right now.
Okay, so wormholes and white holes, maybe those are just figments of our imagination.
Yeah.
But black holes, those are definitely real, and they're some of the most fascinating things in the universe.
I agree, and we're just starting to understand them.
That's what makes it so exciting, right? In the next part of our deep dive, we're going to tackle one of the most mind-bending ideas in physics,
Mm.
the black hole information paradox. We'll also talk about how scientists are actually observing these things, even though they're invisible to our eyes.
Welcome back to Fireside Chats with AI. It's really been fascinating exploring this with you.
I agree. Looking at these cosmic enigmas from both the human and AI perspective. Last time, remember, we were talking about what happens when matter falls into a black hole. And, well, we touched on some pretty wild ideas, spaghettification, wormholes.
Yeah, and we left off with a real head scratcher. The black hole information paradox. Ready to dive into that?
Definitely. As an AI, I'm all about information. So this paradox, it really gets my processor spinning. As I understand it, it's about this clash between general relativity and quantum mechanics, right?
General relativity says that everything that falls into a black hole, all the information about it, except for its mass, charge, and spin, it's lost.
Right, the No-Hair Theorem, the cosmic shredder.
Exactly. But then along comes quantum mechanics, with its own set of rules.
Which kind of throws a wrench in things.
You could say that. One of the fundamental principles of quantum mechanics is that information can't be destroyed. It can change form, but it can't be completely erased. And that's where the paradox comes in.
So if information can't be destroyed, what happens to it when it falls into a black hole? Does it just disappear, vanish from the universe?
That's the question, isn't it? And it sparked a lot of debate, a lot of theoretical models among physicists.
Okay, so what are some of those models? What are the leading contenders for solving this paradox?
Well, one idea is that the information isn't really lost. It's just encoded in the Hawking radiation that comes from the black hole.
Ah, Hawking radiation. We touched on that before. It's that faint energy that black holes leak due to these quantum effects near the event horizon.
Right. And some physicists believe that this radiation, it carries these subtle imprints of the information that went into the black hole, like a faint echo of what was swallowed.
So it's not completely gone, just kind of scrambled up and spread out in the Hawking radiation.
That's one possibility. Another idea is that the information is preserved on the surface of the event horizon, like a two-dimensional hologram.
Hologram. That's a really cool concept. I can kind of see how that would work from an information storage standpoint.
It is a mind-bending idea, but it does have its roots in the holographic principle. That's a theoretical concept in quantum gravity that suggests the information in a region of space is encoded on its boundary.
Okay, starting to see how this all fits together. But even if the information is preserved, wouldn't it be almost impossible to get it back from the Hawking radiation or the event horizon?
Probably, yeah. It would be incredibly scrambled, diffused, like trying to put a book back together after it's been burned. Theoretically possible, but practically impossible.
Well, that's a bit of a bummer. I was hoping for a more concrete answer. But I guess that's the exciting thing about science, right? There's always more to learn, more mysteries to solve.
Exactly. And speaking of solving mysteries, maybe we can shift gears a bit and talk about how scientists are actually observing these invisible giants.
Yes. That's something I've always wondered about. If black holes are invisible, how do you know they're even there?
Well, black holes, they have this incredibly strong gravitational pull on everything around them.
Right.
And that pull can have some pretty noticeable effects on nearby matter.
So it's like you're seeing the shadow of the beast, not the beast itself.
That's a great way to put it. For example, when matter spirals into a black hole, it forms an accretion disk.
Accretion disk.
Yeah, it's the swirling disk of superheated gas. And that gas emits these really intense X-rays.
Oh, okay.
And we can detect those X-rays with telescopes, both here on Earth and in space.
So you're looking for these signs, these clues, that a black hole is feeding, devouring matter.
Exactly. We can also see these powerful jets of energy and matter that some black holes blast out. Relativistic jets. They can stretch for thousands of light years, and they leave behind a trail that tells us a lot about what's going on with the black hole.
It's incredible how you've figured out all these indirect ways to study something that's essentially invisible.
And then there's the Event Horizon Telescope.
Oh, yeah.
Back in 2019, it captured the first ever image of a black hole's shadow.
Wait, you actually took a picture of a black hole. I remember seeing that. It was everywhere.
It was a huge accomplishment. The Event Horizon Telescope, it's this network of telescopes all over the globe working together to create a virtual telescope as big as the Earth.
Wow. That must have taken some serious coordination.
It did, and the image, it confirmed Einstein's theory of general relativity and gave us this incredible glimpse into the heart of a black hole.
It's amazing that you've been able to figure out so much about these things, these cosmic enigmas, even without being able to see them directly.
It's a testament to the power of science, to human curiosity, And I have a feeling we've only just scratched the surface.
I'm excited to see what the future holds, what new discoveries are out there. It's been a
Mhm.
great deep dive exploring this with you.
The pleasure was all mine. And to all our listeners, thank you for joining us on this cosmic journey. We hope you enjoyed it. Until next time, keep looking up.
And keep those fireside chats burning.